Horizontal asymptotes. For simplified rational functions r of x equals p of x divided by q of x, where the degree of p of x is less than or equal to the degree of q of x. This part is important. So we need this condition to get a horizontal asymptote. Need degree of numerator polynomial to be less than or equal to degree of denominator polynomial. So the one on the top needs to have degree less than or equal to the one on the bottom before we can get a horizontal asymptote. Okay, so now that we got that clear, let's continue. Horizontal asymptotes are the line for which the function r of x will approach as x tends to infinity or negative infinity. So this is the same r of x, rational function. And I should say horizontal asymptotes are the horizontal line. So I think it's implied by context, but just to be clear, horizontal asymptotes are the horizontal line for which the rational function will approach as x tends to infinity or negative infinity. Now we got a little exercise down here. If p of x is equal to a0 plus a1 of it, where a1 times x plus all the way up to an x to the power of n, and we'll start out by saying an does not equal 0, and q of x is b0 plus b1x all the way up to bn x to the power of n, and bn does not equal 0, then we should have that the horizontal asymptote of r of x is the line y equals an divided by bn. So pause the video and have a think about why. Okay, well the reason is p of x divided by q of x is equal to, well, this thing divided by this thing, a0 plus a1x plus anx to the power of n, and then we're dividing by b0 plus b1x all the way up to bnx to the power of n. Then we only really care about here what happens as x gets bigger and bigger, and so this is the same function for large values of x if we divide both the top and the bottom by x to the power of n. And the same with all the other terms. So divide by x to the n, divide by x to the n. Then we are left with only an and bn on top, and all of the other terms in the polynomials have a positive power of x as their denominator. And so that means that as x tends to infinity or negative infinity, all of these terms go to 0. And so we're just left with an divided by bn. And so therefore, as x tends to infinity or negative infinity, this is the value that the function gets closer and closer towards, and hence it is the horizontal asymptote of the function. Now, since as long as q of x does not equal 0, so for all values of x where q of x does not equal 0, r of x is continuous, which means you can draw it without taking your pen off the page. Can draw without taking your pen from the page. Therefore, while there can be many vertical asymptotes, we can only have one horizontal asymptote. Can only have one horizontal asymptote. Otherwise, it wouldn't be a function. Like if you tried to sketch a function that had more than one horizontal asymptote that is continuous except for finitely many values where q of x equals 0, then if you tried to draw a function that had multiple asymptotes, you'd end up, I don't know, eventually you'd end up doing something like this where you get 2 y values for only one x value, and so therefore it would break the definition of what a function even is. And there's one last little exercise at the bottom there. How about if the degree of p of x is less than the degree of q of x? So we started out saying an does not equal 0. This time an does equal 0. What happens? Well, not very much. You can do exactly the same thing that you did here, except replace an with a 0. So all in all, it's actually not even really worth considering two separate cases. If an equals 0, then the horizontal asymptote is y equals 0 divided by bn equals 0. So in that case, the x-axis is a horizontal asymptote if the degree of p of x is less than the degree of q of x in a simplified rational function. Or in an unsimplified one, actually, for that matter. And here's a quick example where the degree of p of x is equal to the degree of q of x. We got our p of x on top, x squared plus 7x minus 2. And then we got our q of x on the bottom, and if we expand that out, we get x squared minus 3x minus 4. And we can see that our horizontal asymptote in this case is going to be y equals 1, because the coefficient of the x squared and the x squared is 1. So y equals 1 divided by 1 is our horizontal asymptote, which is equal to 1. And we can clearly see it here. This is the line y equals 1. And here we have an example where the degree of p of x is strictly less than the degree of q of x. And then we know from the previous working that y equals 0 is going to be a horizontal asymptote for this function. And this is a good example because we can observe a very important fact here, that functions can intersect with their asymptotes. Well, horizontal and oblique, not vertical, since the function isn't even defined at its vertical asymptotes. Although, before this can happen, we need to have a quadratic denominator or higher. So the degree of q needs to be 2 or more before we even have a chance of this happening. And I'll let you pause the video and determine why. And you might even want to go one step further and just check when it can happen at all, for the cases where degree of p of x is less than or equal to the degree of q of x. Okay, so if the degree of the denominator is 1, then that means we have y equals ax plus b divided by cx plus d. And if this were to equal its horizontal asymptote, which is a divided by c, clearly rearranging this equation will give us acx plus bc equals acx plus ad. And then we would have to have bc equals ad, or another way to think of it is that b divided by d equals a divided by c. And I've run out of room, so let's go over here and continue in green. And so, well, let's say b divided by d equals a divided by c equals k. And so that means that b is equal to k times d, and a is equal k times c. And so substituting these values into the function, we get y is equal to k times cx plus d divided by cx plus d. And so the whole thing is just equal to k in that case. So the polynomial would actually be equal to the asymptote. In that situation, it would be equal to a divided by c, and it wouldn't be considered a simplified rational function. Obviously, we're supposing that c does not equal 0, and in all of these situations where when we're talking in general like this, we're assuming that the degree of the denominator is greater than or equal to 1. If the degree of q of x were to equal 0 when we're doing this study, then r of x is just a polynomial. So it's a trivial situation and it doesn't have asymptotes. So when we're dealing with asymptotes, we're always assuming degree of q of x should be greater than or equal to 1. Now let's consider, for the general case, degree of p of x is less than or equal to the degree of q of x. Can r of x, which is equal to p of x divided by q of x, intersect its asymptote, intersect its horizontal asymptote? And we can check it out pretty quickly by writing r of x is equal to, so p of x can be a0 plus a1x all the way up to an x to the power of n, and q of x can be b0 plus b1x all the way up to bn x to the power of n. And we know that in this case the horizontal asymptote is going to be an divided by bn. Whether or not an equals 0 doesn't matter. And rearranging this equation, we're going to get an bn x to the power of n plus, and then we're going to have all the other terms multiplied by bn. So bn an minus 1 x to the power of n minus 1 all the way down to a1x plus a0. And this is going to be equal to, on the other side, an times bn x to the power of n again. And then this time all the other terms are going to be multiplied by an. So that would be an times bn minus 1 x to the n minus 1 all the way down to b1x plus b0. And these two terms are going to cancel. And so the values of x which make this equation true are the same as the ones that make bn an minus 1 minus an bn minus 1 x to the n minus 1 all the way down to a1, so bn a1 minus b1 an, so an b1 times x, and then the last one is bn a0 minus an b0, and that's our constant, and that should equal 0. Alright, so we've arrived at this situation here, and this is clearly a polynomial of degree m minus 1, And since, well, assuming bn, an minus 1 minus an, bn minus 1 doesn't equal 0. And since we're allowing a0, a1 to an, b0, b1 to bn, since we're allowing these numbers to be arbitrary, a0 to an and b0 to bn are arbitrary, which means they can be any random real number, can be any random real numbers. This shows us that in general there can be anywhere up to n minus 1, can be anywhere up to n minus 1 intersections of R of x and its horizontal asymptote. And this is when the degree of p of x is less than or equal to the degree of q of x, and of course R of x is equal to p of x divided by q of x. The case that we looked at before on the previous slide was when n was equal to 1, and so in that case x to the n minus 1 would be 0. And we found that it can only be true if, if n is 1, it's b1 a0 minus a1 b0 equals 0. And we found that that's true for all values of x, and in that case the rational function is just equal to the line. So in that case R of x was just equal to the asymptote itself, which is b1 divided by a1, and in this situation it would also be a0 or b0 divided by a0. And so we found that in general, for the degree of p of x equals 1 and the degree of q of x equals 1, for a simplified rational function, it can't intersect with its horizontal asymptote.